As Jens said before in Remo, my name is Zach, and I'm a Boost author and C++ Standards Committee member. Now I'm part of the Boost steering committee as well. And this is a talk about this particular library that I've written for Boost. It's a part of Boost as of the latest release. But more broadly, it's a talk about how to make our lives easier when we're dealing with the STL and how to write interfaces to the STL, iterators, views, and containers, as it says in the talk title, in a way that we can get a lot more done and still have these nice interfaces. Okay, so first let's talk about iterators. So iterators, of course, as we know, are like sort of the glue that holds together the STL. So it's the way that containers talk to each other. It's the way that containers talk to standard algorithms and standard algorithms talk to containers. It's often very nice to have your own iterator type for something that you've written. So if you've got some container-like type or even some view-like type, you might want to have an iterator for it so that you can get that nice interoperability. So you can talk to standard containers, talk to standard algorithms, and so on. But unfortunately, that's pretty difficult right now. And that's because there's these big tables in the in the standard that tell you, like, to make this an STL compliant iterator or container or what have you, you have to have all these parts of the interface, right? You have to have all these expressions that are well formed for that type. And that's usually a lot of work, and it's a lot of testing burden if you want to get it right. Okay. So the point of Boost.STLInterfaces is to make that process of writing those types a lot easier and take something, especially in the case of iterators, that's really laborious and a lot of heavy lifting. And there's even some subtleties you can get wrong and make those things much easier. Okay, so let's jump right into an example. So this is an iterator that I wrote for a library before it had Boost.STLInterfaces. And the type that this was an iterator for was a repeated string view. So imagine you have a string view and a parameter n, and you want to repeat that string view n times. So the view is as if you had a string with that whatever few characters are in that string view, that repeated n times. But of course, it's a view, so you just have the string view itself, and then when you get to the end of the substring that you're repeating, you just loop back around to the beginning, and you keep doing that over and over n times. Okay, so it's random access because you can use the modulus operation to jump to any repetition of that substring and then go to the right element within that repetition, right? And this is the iterator that I wrote for that. Okay, so let's take a look at this. So first of all, we've got a bunch of using declarations at the top. These are the nested type defs you have to have in any iterator. Then we've got the default constructor construction from the underlying const char star, and then we've got dereference and index and blah blah blah. Right? I'm just going to scroll through it now. We can see all these operations here, and it's a lot of it. So, like I said, it's a random access iterator. So we've got a lot of operations. Right? These are the relational operators. We've got free, plus, and minus. Okay, so that's a lot to do. So once I had Boost.STLInterfaces, I rewrote it, and this is the rewrite. So first, I inherit from this CRTP base iterator interface. And for those of you who don't know what CRTP means, I think many of you probably do already, but what that means is the curiously recurring template pattern, right? So this is the name of the type we're making. This is the base class we're deriving it from, and this is the derived type, again, that's the class we're making, repeated as the first template parameter, okay? And the reason we do that is because this base class is going to use operations from this derived class to do other operations. So in order to know what operations are in your derived class, you don't normally have visibility of that within the normal rules of inheritance, so you need to have that derived class as a template parameter. So that's the mechanism that allows CRTP to work. And then you've got the random access iterator, the tag that integrates the random access iterator. This is the value type, and this is our reference type. It just so happens that for efficiency purposes, I didn't want that reference type to be an actual language reference. I didn't want it to be char or ampersand, just because you're passing around pointers to individual bytes, and that's really not very efficient. So it didn't need to be that. I could have left this off, and it would have just defaulted to char ref as the reference type. Okay, so let's look at the actual implementation. So I've got the default constructor, and I've got a constructor from the underlying const char star. And then I've got dereference operation. I've got an offset operation. I can do plus equals, and then I can subtract two of these iterators, one from the other. Okay, that's it. That's all I have to do. It turns out that all of those operations we just saw on the previous slide, you can do in terms of these three operations. These three operations form a basis that you can use to implement everything else. Okay. So when I started using iterator interface to write iterators, and in fact, I had a lot of custom iterators in this other library I was working on. And once I had STLInterfaces, I went and partly to make sure STLInterfaces worked the way I wanted it to, and partly because I wanted to clean up that library and make it more usable, I went back and made all of those iterators in terms of iterator interface. And I found that I fixed a bunch of bugs when I did that. Now, I've actually got two bugs that were on this slide. And I want to show them to you. I put a little space here so I can spot them more easily. But this is the first one. So normally you have a random access iterator, and you can say plus or minus some integral value, right? Plus or minus 3, something like that. But we never write for the iterator IT. We never write IT minus 3. I mean, sorry, we never write 3 minus IT is what I was trying to say. So because I was cutting and pasting, and because there's so much interface here, I actually went and put this operator minus here with the difference type on the left instead of on the right. And that's innocuous in some sense because no one's using this because we don't write code like that. But it's this operation that's there just waiting for someone to accidentally type that in their code when probably they made a mistake. And instead of it being an error in the type system where it said, hey, there's no overload for that operation, I've now got an overload for it, and I've helped perpetuate their mistake. Okay, so that's problematic, and that could have lingered for a very, very long time. The other error is probably worse. I've tried to implement greater than or equals in terms of this less than or equals over here. Whoops. And that's something we do very frequently, right? And we just swap the arguments, but I didn't swap the arguments. So I implemented less than or greater than or equals, and its semantics are just less than or equals. So it's just wrong, okay? Now that's not an operation we do on random access iterators that much, and certainly in my entire library that was using this iterator, I never used that operation. So again, this is an error that would have persisted for a very long time potentially. The only reason that I even knew this was a problem, because I never detected it before I replaced it with something that worked, was that when I first submitted Boost.STLInterfaces to Boost for consideration for, before the review, you kind of say, hey, is anybody interested in this as a library? Someone looked at the GitHub page for the library, and this example is the first thing you see on the GitHub page. And someone said, hey, that operator greater than or equals is just wrong. So the point here is that when you use something that does a lot of the work for you, and you only have to write 3 operations and test them, and you get all the other operations, you're essentially relying on my testing infrastructure where I've already tested iterator interfaces and I know it works, right? And so it's a really nice thing to have, not just because it's less work to do, but because often when there's that much extra work to do, we just don't do it. We don't test every single operation of every iterator we write if we're writing a bunch of iterators. So this helps you avoid those kinds of bugs. So, I just talked about iterators, but STLInterfaces also handles creation of views and sequence containers. And it's really instructive to talk about the views first. So let's look at those first. So first, in case you didn't know this, C++20 introduced view interface. That's in the std ranges namespace. And whenever you want to create a view, all you need to do is make a type that has a begin and end, and then you derive from view interface, and it's the same kind of CRTP pattern. You pass the name of the type you're deriving from view interface to view interface as template parameter, and then it implements all the operations that make sense given that begin and end. And all of the views inside of the std ranges namespace are actually implemented that way. None of the views have anything but begin or end, and they're all derived from view interface. Okay, so as a quick reminder, if you didn't miss, or if you missed this part of the C++20 ranges work, in C++98, we have tons of interfaces that are done in terms of iterators, right? So it's begin and end. And those iterator types have to be the same. But in C++20, they don't have to be anymore because now there's a notion of having an iterator and sentinel pair. Okay, so as long as I can say ++ on the iterator and then compare it to the sentinel at every step, then that works as a sentinel. I don't have to have any other kind of requirements other than equality comparable with across those two things. So as a quick example, here's a null sentinel t, which is my sentinel type, and here's operator equals, okay? So if I have some pointer to char, and I have a null sentinel, I can use this operator equals to figure out if I'm at the end. The way I figure out if I'm at the end is I dereference the pointer, I get the character I'm pointing at, and then if that pointer is null, then I'm at the end. So I don't actually have to know the pointer at the end. I can just know that I have a way of figuring out if I'm at the end. So that means that I can construct a range and start using an algorithm on it immediately without actually running strlen on it, let's say, to find the end. So there is stood ranges distance, part of the ranges namespace. And I can pass it this null terminated string and my sentinel, and sure enough, it tells me that null terminated string is 15 characters long. It had to actually step through the entire thing. So that's an order n operation. It's not as fast as it would be if I had 2 pointers, but I only had to go to the end because I called distance. If I was going to do something else, like let's say putter pointed to 1 trillion characters in memory, and I only wanted to find something I know is in the first 1K, then I just use stood ranges find, let's say, to find the character I'm looking for in the first 1K. And I don't have to do strlen and do 1 trillion steps first to figure out where the end is before I can even call the algorithm when I know that I expect that to be at the beginning. So it's handy in some situations, really handy with null terminated strings in many cases. Okay, so let's look at the view interface template itself. So this is just copy paste straight out of the standard. You give it the derived class here as a template parameter. And it derives from this thing called view base, which is essentially like an inheritance that is used to tag this as a view. There's a mechanism in the ranges library that lets the algorithms know if they're dealing with a view or dealing with a range in case that matters in that particular algorithm. Or I don't actually know if it's particular to algorithms. I think it's other things like making views and so forth that are actually using that information, not algorithms themselves. But in some places, it's nice to know if you've got a view or a range. You do different things in different places. So a range would be something like a stood vector, right? A stood vector is not also a view because it owns the elements that it's a range of. Okay, so a range may or may not own the elements, and a view never does. So all views are ranges, but not the other way around. So then we've got these two convenience cast functions that take the the derived type that we've got, and we cast to that derived type, and that way we can just write that briefly in multiple places. So let's look at one of the members here. We're not going to look at all of them. I think a good one to look at is size. So from a high level of abstraction, what we want to do with size is if this is well formed, if I can say end minus begin, then size makes sense for this begin and end that we were given in the derived type. So as long as that's well formed, we probably want to have a size, right? So the way we figure out whether or not to have size is we put a concept constraint on it right here. And I'm not going to break down what that concept constraint does and how it does it, but suffice to say that if that expression in the return statement is well formed, then that concept constraint means that this is a valid overload, okay? And it's done in terms of a bunch of built-in concepts instead of doing the requires of that expression itself, just because it's trying to use the built-in concepts, okay? So again, size will exist if this is a random access range, and it won't if it isn't, because we don't want an order n size, okay? We've got front here if this is a forward range, because an input range doesn't have a meaningful front. As soon as you ask for the front has changed out from under you, so it has to be at least a forward range. And there's other similar requirements on everything. So the total set of possible operations you might have on a view is it might be empty, it might be contextually convertible to bool. You might have the data member function on it, which gives a pointer to the beginning. It might have size, front, back, or the index operation, okay? So again, all you need to do is put begin or end on your type and derive from this template, and then you get all the operations that make sense for your begin and end. And that is using both the category of the begin iterator and whether or not the end is a sentinel or another iterator, because that also impacts things. Okay, so let's look at a quick example of use. So again, we're going to use this null sentinel t that I showed previously. So my view has a begin that is a const char star and has an end that is a null sentinel. And I'm deriving from std_ranges view interface, and I'm passing myself as the template parameter. Okay. Now we have these constructors here. Those are totally optional. We could have made this public and just, brace initialize this thing, but we have a default constructor and we have a constructor from a pointer. And then, as you would imagine, because I have begin and end, and because there's a range overload of std_ranges distance, I can just call std_ranges distance, and that works just fine. And that completely makes sense just lexically looking at it. I have a begin and end there, so that makes sense. But then what is implied by the inheritance from view interface is that I also have front and the index operation, which I did not write. So you get all the other operations for free, and that's really nice. And again, this is the way all the views in the std_ranges namespace are implemented because of this nicety. Because that way they can be generic, and you don't have to know for one particular view what happens if it's a view where the iterators it's using within the view are random access or forward or what have you. Okay, so STLInterfaces has an implementation of view interface. If you're compiling in C++20 mode, of course you don't need that. It's in std_ranges. So it does have support though via Spine instead of concept constraints for C++14, C++17. So if you want to use that same approach as far back as C++14 code, you can do that with the library. So it doesn't add anything new. It just sort of backports something from the C++20 standard. So now let's talk about iterators. That is, I think, probably the most common use case for the library. But if you want to use view interface, that's great. But I mean, the thing that made me want to write the library from the beginning was iterators, and I think they come up a lot. So there's a lot of reasons why you might want to write one. Maybe you want to write a checking iterator. Visual Studio has these really nice checking iterators. You catch lots of bugs that you didn't even realize were there by using these checking iterators. You might want to write something like that yourself. You're using a different compiler or a type for which there's not a checking iterator of theirs that you can use. You may have a legacy data structure like a linked list from some old C code that you have to use. If you have something like that, it would really be nice if you could use find and find if and mismatch and all the standard algorithms with that linked list without having to sort of rewrite them yourself to use the linked list. If you could just write an iterator that you used instead for those, that would make your life a lot better. And then there's also other cases where you just have like sort of a specific one-off use case where a particular iterator would be really nice. And we're going to talk about one of those use cases right now, an ad hoc use case. And this is something in particular that I did in another library where I wrote this iterator for internal use within an algorithm and I never reused it again. So let's say you have two sequences and you want to treat them as if they're one big sequence. So you want to do some operation or operations over the entire thing all in one go, okay? So as an example here, let's talk about find. So let's say I have these two sequences. I've got a vector of int and I've got a list of int, and I want to basically do find, okay? So I'm going to write find again, which is terrible, right? And the way I have to write it is not great either. So essentially I have to take the first and last of the first range, and then I take the first and last of the second range, and I do std find within the first one, and then if I don't find it, I do std find within the second one. And in either of those cases, if I do find the result I'm looking for, then I need to return them somehow, but they're different types, so I end up using like a std variant, boost variant, something like that. And then when I get the result, if I compare it to end, I have to reach into the variant and get the right alternative. I don't even know if it's the second alternative, so I have to actually ask. I mean, it's really clunky. An alternate interface I could write would be to return a pointer to the value that I was trying to produce instead of an iterator to it. The problem with that is that the reason we use iterators in the STL is that then I can resume the search if I want to find something, and then from there find the next instance of that element within the sequence. I can't do that if I've got a pointer, because now I've lost the ability to go back to an iterator to call find the next time. So there's not a lot of good alternatives here. And again, we're having to rewrite find. We don't want to rewrite find. And what happens when we want to change find to find if? We have to rewrite that or write another one. So we don't want to be in the business of rewriting the standard algorithms. We want to write iterators that let us use the standard algorithms. So one alternative is that, again, you just write an iterator for that that spans that whole pair of sequences. And the range v3 library from Eric Niebler, a lot of you probably already know this, but Eric Niebler is the main person behind the std ranges work. It has this thing called Concat view that's not in the std ranges namespace. It might land in some future standard, but for now it's not in there. And it does exactly what we want it to do. So if I say ranges concat, and that's the range v3 library ranges, not std ranges. So I say ranges concat vec and list, I get a view over the whole pair of sequences, right? So from the beginning of the first one to the end of the second one. And then I can say std ranges find on that and find 42, and I find it or I didn't, okay? It's very nice. And this iterator that it creates for us is some concat iterator implementation detail. I don't need to know that much about the iterator. I just say, auto, whatever that iterator is, and it acts like an iterator with all the right properties, and that's all I really need. Okay, so sometimes you can't use ranges concat. It might be that you want to use, you want to write a code that has as few dependencies as possible, and you can't bring another dependency. Ranges v3 or range v3 is a pretty big library. Maybe you don't want to pull that in. I was writing code for Boost, and I literally couldn't pull in range v3 without, I guess I could have cut and pasted a bunch of code and then asked Eric to relicense it, and that would have worked, but it would have been clunky, right? And there's other reasons why you can't use ranges concat, even if you have access to the range v3 library, and that is the two sequences have to have what's called a common reference. So if I take a reference by dereferencing either an iterator to either range, I get a reference, and if I take those two references from the two ranges, I had better be able to make a common reference out of them using std common reference with. Okay, if I can't make a reference between the two types and the two sequences, even if I have an easy way to make them to view them as the same type, then it doesn't work. So in this case, I've got my int, and my int is some strong type def that I want for some reason. We've all seen strong type defs in people's code probably. Sometimes they're more trouble than they're worth. Sometimes they're really useful. But here I've explicitly, or I made the constructor explicit. So I have said outright, I do not want implicit conversions from int. And of course, I haven't provided any implicit conversion to int. And so there is no common reference because those two types are not, there's not some built-in conversion or anything either. Now, I do have this nice projection. I can say as int on an int or as a myint, and I get an int out because they're both fundamentally just a thing of the size of an int with the same semantics as an integer. But that doesn't help me because even though I can use projections in the ranges algorithms, I have to say ranges concat first, and the projection is not in play in ranges concat. And so there's no way for me to bridge the difference between those two types, myint and int. Okay, so put a pin in that one. We're not going to talk about that directly now. We'll talk about it in a minute. So now, as I was alluding to before, if you just want to find a value, if you're just re-implementing std find, you would do it on the first range and then do it on the second range and return the result of whichever one you found the value in. What happens, though, when your algorithm actually looks at more than one element at a time? Now you can't just partition the work into do it in the first range and then do it in the second range. Reason being that some of the work might span both ranges, and you have no way of dealing with that. So that's another use case why concat or something like it might not work. Okay, so it turns out for my use case, I was writing code for Boost, and I couldn't use the range v3 library for essentially all the reasons I just stated. I didn't have a common reference type. I didn't have access to range v3 at all, and I had an algorithm that spanned multiple elements at a time. Okay, so the way I solved the problem with no common reference is I just provided this template argument, template parameter rather, to concat_iter that says this is the value type. So regardless of what the underlying ranges were, I'm asserting this is the value type. So however I get there is my business, but I know that I can form a reference to whatever the value type is because I don't have to use common reference machinery to get there. I just know the type a priori. And then, of course, I'll get the first range and the second range as template parameters. Now, this is going to be a proxy iterator. We will talk about what proxy iterators are in a minute, so don't get too caught up on that. But suffice to say that this is a template alias to iterator interface that makes it easier to write proxy iterators. It is not its own template or anything. It just has a nice set of defaults for instantiating an iterator interface. As before and as always, I pass my own type as the first template parameter. I indicate it's a bidirectional iterator, and then I provide the value type here. Okay, so the iterator itself has type defs for the two kinds of iterators, the iterator to the first and second sequence, and I'll get this little end tag type here. We'll see what that's used in the constructors in a second. So I've got default construction, and I've got construction from an iterator in the first range, and I've got another constructor that constructs at a position that's in the second range. Now, because first iterator and second iterator might be the same type, that would be ambiguous. So I disambiguated it by adding this little end tag thing here. That's all that's there for. Okay, so with that in hand, all I need to do is implement the pre-increment operation, the post-increment operation, and then what else we need? Decrement and dereference rather, and equality. Okay, and because I implemented an operator plus plus and operator minus minus inside this class, I'm hiding the other automatically generated overloads for the the operator plus plus int and operator minus minus int. I'm hiding those names because they have the same names in the base class, so I have to have using declarations here to pull them in. Okay, so anytime you have an operation that another overload of that is generated by the base class, you have to do this when you use this these views. So the operation itself is pretty straightforward. If I'm in the first range, then I increment, and if that takes me to the second range, then I tag that I'm in the second range, and if I'm in the second range, then I just increment the second one. Right? It's very simple. The minus minus operation just does the same thing in reverse, and that's it. That wasn't much code to write. Okay, now to actually use concat, so I needed the iterator to do the work, but now I want the concat view and the concat function, right? So the concat view, as you would imagine, is going to use view interface, and its iterator type is just going to be the concat iter that we just looked at. I can construct one from a pair of iterators and then begin and end, just use a pair of iterators. And whatever other operations I may have on the view come from the base. I only have to specify begin and end. Now, concat itself is interesting because, again, I have to specify explicitly this template parameter t, and then I give these two ranges. Now, for my use case, I wanted to always use references to existing ranges. I didn't want any dangling cases. These don't have to be this way for code you were going to write, of course. You could make them forwarding references if that makes sense. And then I just create a concat view out of an iterator to the beginning of the first range and an iterator to the end of the second range, right? And that's it. And then I of course, need that tag to disambiguate the second range case. And here's it in use. So if I've got a vector and a list with those numbers in it, I use concat and I say this is an int, and I concatenate those two things and I get this view v. And then within v, I can try to find 42, and I find that it's not there. And I try to find 58, and then I find, oh, it is there, and it's in the second element. Okay, right there. That's exactly what we'd expect. It all works very nicely. Okay. Now, the reason I brought up that thing about myInt and int before is that we could have given concat a projection, and then we could have passed that projection into the iterators, and then we could have regularized the type that is returned over a sequence of myInt and a sequence of int. So, whoops, here, if I put the projection right here, and then I would probably pass the projection in like right after the iterator parameters here and here, and then inside the iterator itself, I would use the projection when I did this dereference and did this dereference. And so if this returned to myInt and this returned an int, after doing the projection, after calling that as int function on both sides, or on either dereference, I should say, then we get back an int, okay? So the reason I point this out is because that really does give us the kind of flexibility that doesn't belong in a general purpose concat operation, but it makes sense in our use case maybe, okay? And what's so useful about that is that we just saw an amount of code that is very reasonable to have to write to get the kind of functionality we want and to get the reuse of all of the standard algorithms. And it's really nice. So this iterator I used within an algorithm that itself used a bunch of STL algorithms internally. And the fact that I didn't have to rewrite all of those is basically the justification for writing this code. And I didn't have to write a lot of code to get there. So it's very nice. And you have the kind of flexibility to write one-off iterators when you don't have to write a tremendous amount of code. You saw I only had to write like 4 or 5 operations for this one, 3 operations for a random access iterator. So it's a very small amount of work. Okay. So now this is the thing I was saying we're going to get back to. Let's talk about proxy iterators. So so every iterator has a nested typedef reference, okay, like spelled reference, ref, erence. It may or may not be a language reference. It may be something ampersand or not, okay? If it's not, that is considered a proxy iterator. And a reason you might want to have that is, let's say you're implementing std ranges iota view, okay? So iota view is iterating over some sequence of integral values, right? From 0 to 5 or from 0 to infinity. And at each step, it generates a new number just by adding 1 to the previous value. There is no underlying sequence to generate references from. So it's going to give you a value, not a reference, every time. So it's got to be a proxy iterator. As another example, if we've got a transcoding iterator, an iterator that converts from UTF-8 to UTF-32, let's say, you are going to generate integers, unsigned integers, something like that as the return type, maybe char32, whatever it is. But the return type also cannot be a reference because there's no underlying char32 or int or whatever. There's a sequence of bytes that you're using to construct that value. So again, you can't construct a literal language reference as the reference type, the nested namespace, or sorry, the nested typedef. So there are some oddities to that. When you have that, you have to do something weird when you do the arrow operation for an iterator. And so the weird things that you have to do are just sort of handled for you automatically by STLInterfaces. And you don't have to do any heavy lifting there. And so as an example, here's zipiter, which is kind of the canonical example of a proxy iterator type. So we derive, again, from proxy iterator interface. We pass ourselves as the first template parameter. It's a random access iterator. This is the value type. So sort of abstractly, what are we iterating over? We're iterating over a tuple of ints, right? We never actually use this type directly, but that's actually pretty common with value type, is that sometimes you have a value type that you don't actually use in practice. I think std map has a value type of key comma value, but you never actually see that in a std map. It's always const key comma value. And then here's the thing that does the real work. This is the reference type. So when we dereference one of these iterators, this is what we get. And it is a tuple of references, not a reference itself. So again, we have default construction. Just to keep the example really simple, the only thing we're iterating over is pointers to ints. So it's two sequences of integers. And when we do the dereference operation, it's really simple. We just dereference both sides, and we take the resulting reference, and we pass that back as a tuple, right? Or both resulting references, pass them back as a tuple. And then we have the offset operation with plus equals, and we just do the same offset operation in lockstep on both underlying iterators. When we want to know how far apart they are, we just subtract the first iterator on one side from the first iterator on the other side. And that's it. That's the whole thing. Okay. So again, zipiter's reference type is not itself a reference. It's not std tuple something in angle brackets ampersand. It's std tuple and the members of the tuple are references. Okay, so that's different. That makes it a proxy iterator, of course. And this is okay with the iterator concept. So if you look in the concept for forward iterator and random access iterator and so on in C++20, they say nothing about whether or not the reference nested typedef needs to be a language reference or not. They just don't address it. It's not important. In C++98, there's these big tables of the requirements for an iterator, and that includes nested typedefs and so on. And it does explicitly say the nested typedef needs to be, if the value type is t, it needs to be t ampersand for all iterator categories past input iterators. So if you are forward or higher, you have to have a reference type, a language reference type for that reference nested typedef. Okay. So that means if you write something like zipiter, you're supposedly not supposed to be able to use it with the standard algorithms from C++98. But that's only technically true. In reality, because the 98 algorithms don't do any kind of concept checking, because they just use the operations that they're given. They tell you what the operations are in a table in the standard, and then they know that they're allowed to use those operations, and that's it. They don't actually check. So in effect, if you have all the operations, you can just use that type, and it doesn't matter. I've never seen anything in any standard library that works against that. So the reason I bring this up is because people will say, well, proxy iterators are dangerous because they're technically not the kind of iterator you're advertising. If you say random access, they're not. They're just an input iterator. But effectively, we don't care. And I even made this work with std sort. Now I had to specialize iterswap for the particular iterator that I was using to get std sort to work, because std sort, if you just use the built-in iterswap, it doesn't know that it should look inside the tuple at the two elements and swap them element-wise with the other tuple that it's doing the iterswap with. And I think that std iterswap is not a customization point in the one in the std namespace is not, but the std ranges one is. I have not tried getting std ranges sort to work this way. I think that it works, but I have not actually tried, so I don't know that for certain. But I'm only pointing this out just by way of saying, even algorithms that use random access, the random access features like very, very completely, like use many, many of the operations of random access iterator, can still be made to work even though the iterator itself is a proxy iterator. So for what that's worth. Okay, so now let's talk about the other thing the library does, which is make it easier to write sequence containers. So as an example, there's some interest in the standards committee in standardizing static vector and small vector. And what those do is that static vector is a vector where the capacity is entirely within the object. So it never goes to the heap. Whatever size buffer you're using, you pass a non-type template parameter n, then that's the number of elements you can have in the buffer, and then that's it. If you run out of space, you run out of space. Small vector has a buffer size that you also specify with a template parameter n. But then if you run out of n elements, if you add n+1 elements, then it goes to the heap and does some allocations. And of course, vector always allocates on the heap. So we're going to talk about static vector because it's not exactly like vector. It doesn't have all the allocator aware stuff, so it makes a smaller example. So let's talk about that. First, let's look at the synopsis for vector. This is, again, straight from the standard. There's a huge block of type defs. There's a bunch of constructors and special member functions. All the iterators, there's like 12 of them, which is kind of bananas. There's just operation after operation. You can see there's tons of overloads of the same operation in many places, right? It just keeps going and going. Okay, so there's a lot there. So if I was going to implement a std vector-like type, this is all the stuff that I would have to implement. Okay, and there's a lot of redundancy there. Like I said, there's a lot of overloads, and a lot of the overloads can be implemented in terms of some other overload. There's actually a lot of redundancy across the different sequence container types, though. So for instance, if you look at vector assign, it's almost identical to dex assign and lists assign and so on. Not the associative containers maybe, but all the sequence containers essentially have this exact implementation. You take the input range first and last, and you essentially copy from the range first last, you copy that into your existing space as long as there's space to keep copying, or as long as there's input to be had. So once you're done with that operation, you either have extra space that you didn't need that's just laying around, and then you erase that, or you did not have enough room to copy in all the input, and then you just do insert with the rest. Okay, so this is basically what you would do all the time for assign for all the sequence containers. Well, all the sequence containers that are mutable, like obviously the second part of this with erase and insert doesn't make sense for std array, for instance. Okay, so you have to have begin and end and erase and insert for all the sequence containers. You also have to have assign for all the sequence containers. Interestingly, you could have a generic assign that would work for all the sequence containers except for the immutable ones like std array, and it could have its own overload that was specific to it. But you could implement assign one time and have it work for almost every sequence container, and it wouldn't have to be a member. And I think that's pretty interesting. In fact, it turns out there's a lot of the API of sequence containers that could have been implemented that way. A pretty good reason for why they weren't was that at the time, you would have had to use tons of sphenate constraints and operator overloading, and it possibly could have been very expensive in terms of compile time, and it would have been like not the way people generally wrote code when it was standardized in '98. So it's understandable that it didn't end up that way, but it's interesting that if there were a different, an update of the STL at some point where we had sequence containers invented from scratch, I think this would be a better way to do it with a bunch of free operations for most of the operations. Okay. So Boost.STLInterfaces has this sequence container interface that lets you work with sequence containers. So it's directly analogous to view interface and iterator interface that we've already seen. And it really, really dramatically reduces the amount of boilerplate you have to write. So this is an actual implementation of static vector, and this is from I think this is one of the examples in the STLInterfaces documentation. So again, we've got static vector, we say the type we want, and the fixed size capacity that we want to use. We derive from sequence container, and we pass ourselves to the first template parameter. Now, there are some details of the implementation of sequence container interface that are going to be different depending on whether or not the underlying sequence, or I shouldn't say the underlying sequence, the container itself has a contiguous layout, okay? In C++20, I can tell from the iterator types whether or not it has a contiguous layout because the iterators will be contiguous iterators. But before that, I need you to pass me this little tag value that says it's contiguous or non-contiguous. So that's why that's there. And then, so we've got our using declarations or type defs here. We've got a bunch of special member functions and constructors. And then here's the real meat of the operations, right? So essentially, all the stuff that you write that's not a type def or a special member or constructor is right there, right? And it all fits on one slide. So that's a pretty dramatic improvement over what we saw previously. And then, of course, when we implement several of these operations, we need to also say that the operation that we implemented, there's some overloads we need to pull in from the base class, so we have to use some using declarations here, just like we saw earlier. Now, this one's a little bit odd. We've got in place back here, and as you can imagine, like if I've got in place, which I do on the next line, why doesn't the base class just implement in place back in terms of end and in place, right? That makes sense, right? So put a pin in that. We'll get back to that in a second. So if you look at everything that's in that template, you find that there's only 22 functions implemented. 39 of them are not there. 39 of the original 61 from the non-allocator aware vector operations are gone. And that's pretty amazing. So we're only having to implement about a third of the entire sequence container to write a full sequence container. Also, a lot of those were constructors and special members. And because of the rules regarding inheritance, we couldn't get away with getting those from a base class anyway. So we pretty much have to write those no matter what. And just as importantly, most of the operations, now you might want to do something with the special members, like assignment, construction, or copy construction, move assignment. Those four, you might want to do something special depending on the details of your type. But all the others you're going to implement in terms of other automatically implemented things. So there's one that's like a range constructor that takes a first and last of elements, and you're just going to use assign for that. There's another one that takes a parameter n, you're just going to use a resize for that, and so on, right? Or I take that back. I think not resize, but I think there's I forget what it is, but there's an overload, one of the other overloads that's supplied that gives you that for free. So the point is you don't have to actually do any real work with those. That's pretty much just boilerplate. And I really wish I could do that boilerplate for you, but unfortunately, because the rules are inheritance, I just can't. So when you go from I have to write 61 functions that I have to test and make sure that they work, to I only have to write 22, and I'm only doing any actual implementation that needs testing in something like half of those, now it becomes a lot more palatable, a lot more interesting as sort of a maybe not day to day, but as a more frequent operation to make proper sequence containers. So let's talk about in placeback. Placeback was the sort of odd one out in that interface. So the reason in placeback is there is it's actually a hint to the base class template that pushback and popback are efficient, and you should add those. I could have made those just extra template parameters, but in keeping with the sort of automatically detecting stuff, this seemed like a more natural way to do things. So if I had put in place front, it would have added push front and pop front as well. But because I was implementing a vector-like type, I know those are not efficient, so I didn't put in place front. If I had been making a deck-like type, I would have put that. If I was making a stood array-like type, I would have put neither. Okay. And it turns out that if you have any of the operations that are automatically generated by the CRTP base, by the sequence container interface, and this actually applies to the view and iterator interfaces as well. If any of those operations, you know that you have a short circuit way of doing that better, you can just implement that function and it will hide the name of the function from the base class. And so you've effectively like overridden that by just supplying it. And so that is, so as an example, the assign that we saw before. So that's the assign you're going to get if you inherit from a sequence container interface. Now, if you decided, oh, well, I have a way of just directly assigning stuff, then you would just put your assign in your drive type and just implement however you want, and it hides the other assign, and no one knows that it's there and never gets used, and everything's fine. Okay. So we often write types that have within them a sequence of stuff. And frequently, the only way we sort of accommodate the STL requirements for a sequence container is we will put a begin and end on there if it's convenient. And by convenient, I mean usually that boils down to if there's a pointer that I can return from begin and a pointer I can return from end, then I'll add a begin and end. And then now it will play nicely with the standard algorithms and stuff. Now that you have iterator interface, you can now make more complicated iterators and provide that begin and end interface. But just as importantly, you can make that entire type look like a sequence container with a substantial amount more work, but not just a killing amount of work like you had to do before. It was just way too much. I honestly had never written a sequence container from scratch because it was too much, right? It was too much to write just so I could have the same interface as the STL stuff when often we don't use the entire interface. But now that it's easier, I'm hoping that people will find more reason to write more sequence containers and get good stuff out of them. And like I said in the last bit down here, that gives you a nice interoperability story with other things. So in a generic context, you can write a deck or a vector or your my type foo that is also a sequence container, and it all works the same. And I can use the full interface of sequence container in that generic context. So another aspect of this is that because you can write your sequence container one time, it is my hope that people who actually write sequence containers won't write them with allocator support. That it's actually about the same amount of effort to write an entirely new sequence container, or maybe two, than to add allocator support to an existing sequence container. Many people have low to no experience writing allocator support into things, and there's a bunch of subtleties you can trip over. So that's one problem, is that you can make these subtle allocator bugs into your code that are lurking there for a long time and bite you later. It's hard to get right, and it's somewhat hard to test as well. Now, even the people that are real experts at writing allocator-aware containers, I think, should reconsider doing that in the way that allocators are currently supported in the STL. And the reason is that they make your type too flexible. They change the underlying semantics of the type pretty dramatically. So let's just think about insert for a second. Okay, so you've got insert, which takes some sequence of values and sticks them into some arbitrary place within your sequence. For a stood vector, what you're going to do is you're going to say, well, I know how many things I'm inserting. Let me go to the heap. And I know how much capacity I have. And if I know if I spill the capacity, then I know that I need to go to the heap and allocate the one buffer that I need for everything I have and everything I'm inserting, and I copy the prefix, I copy the inserted stuff, then I copy the suffix into this new buffer, and I'm done. Easy. For static vector, you want to do things completely differently because you know you've got a fixed capacity. So you either want to make a side buffer and copy everything into that and then copy back, which seems like kind of a waste. Or more likely, you want to take the stuff that's in the buffer now, that's the suffix, and you want to copy it to where it's going to be. You want to move it essentially to where it's going to be, and then you want to put the inserted stuff in the gap. Okay? You can't write one insert that does that both ways because insert doesn't know how the allocator works, and it doesn't know if you are using an allocator that makes your std vector effectively a static vector, or if you're using the default allocator and it's effectively a std vector in the typical use case. There's yet another algorithm you might want to have if you have the semantics of a small vector and you've gotten there via an allocator. That leaves aside a perhaps even more important issue, which is that move construction and move assignment are completely different for those two types. So if I've got std vector, I know that move assignment and move construction are just swapping 3 pointers. Okay. If I've got a static vector, I know that it's always a copy. And I know that that changes the no except properties of those two operations across static vector and vector. And I know that it also means that one's an order 1 operation, one's an order n operation. So if I write those as different types, then I'm communicating to the user that these things have really different semantics. You need to be aware of that. And if I call them all std vector and I'm allowed to change the allocator to be so radically different, then I'm advertising to the user, these are all 3 instances of the same basic idea. They model the same concept with the same, hopefully the same semantics. That's part of the idea of a concept. But they don't. I have changed the semantics out from under the user. Okay, so let's talk a little bit about future workflow libraries. So first thing would be to, as I said before, I've got the backport of view interfaces to C++ 14 and 17. That uses SVNA. In fact, all the stuff in the current release of the library uses SVNA. So it'd be nice to put concepts in instead. And that's actually done. That work is finished. And it's on GitHub if anybody's interested in playing with that. That will probably land in the next Boost release. So the way I've decided to make that work, so I've got 2 modes. So I've got the SVNA constraints and the concept constraints. Those 2 modes are provided in different namespaces. So I've got the V1 namespace, which is the old namespace for the old constraint mechanism, the SVNA mechanism, and the newer concept stuff is in V2. Now, when you build in a pre-C++ 20 mode, what you get is the V1 namespace gets inlined. When you build in C++ 20 or later, the V2 namespace gets inlined. And it's not quite that simple. If you have to be building a C++ 20 and the compiler has to advertise that it actually has the ranges library with all the concepts in it and stuff. So it's not going to break your code if you're compiling with a compiler that doesn't have that yet. So the result is that you can just write Boost.STLInterfaces foo for any template foo, and you're going to get the V1 or the V2 silently without changing any of your code, depending on which mode you're building in. Okay. By the way, some people might hate this idea, so this is something you can turn off with by building with a macro turned on that disables it. But I think it's going to work out well for most people because I think a lot of people are going to want to use whatever constraint system works the best. And honestly, the concept one works better. You get better error messages and stuff. They're not dramatically better, but they're easier to follow in most cases. So making this transition easier for people, I think, is an important library feature. Okay, another thing that I had considered doing, and I might do in the future, is supporting other container types. So in particular, associative containers. So map, set, multi-set, that kind of thing. The problem is that there's this node interface on the sequence containers, associative containers, is part of the associative container set of requirements. The node interface lets you get nodes out of an associative container, put nodes into it, and so forth. That means that if I were to make an associative container interface right now, and it actually met the requirements of the standard, it would only let you implement exactly things that are like map and set. They would have to be tree-based or at least node-based associative containers. And so that's not really interesting because we already have those, right? Why would I implement another one? But what was use a different tree? Use AVL instead of red black. I mean, it's not a useful thing to have around. So as soon as I got there, and because it's got such a huge interface, I thought, well, I don't know if I really want to do this. So if there's a lot of interest in it from people, if people want to write things like flat maps and stuff, then maybe I would implement one that didn't have the node support if that was, again, interesting to people. But so far, I have an idea for it, but I haven't done it yet, and that's something that might happen in the future. So with that, I think we're wrapped up, and I think we'll do the Q&A. So I am currently in the StreamYard mode, and if you'll give me just a moment, I'll go over to Remo, and we'll do the Q&A there. Thanks.